Have you ever stopped to wonder what holds our world together? Beyond the reach of our senses there exists a fundamental force, an invisible hand governing the interactions of matter at its core. This force, known as the electrostatic force, dictates how charged particles attract or repel each other, shaping the very fabric of our universe. From the lightning bolts that illuminate the sky to the intricate bonds holding atoms together, the electrostatic force is omnipresent, playing a crucial role in countless natural phenomena. But how do we understand this invisible force? How do we quantify its strength and predict its behavior? The answer lies in a fundamental law of physics, a cornerstone of electromagnetism known as Coulomb's law. This elegant principle, discovered by the French physicist Charles-Augustin de Coulomb in the late 18th century, unveils the secrets of the electrostatic force, providing us with the tools to comprehend and predict its influence on the world around us. Coulomb's law, in essence, quantifies the attraction or repulsion between two electrically charged objects. It states that the force between 2 point charges is directly proportional to the product of their charges, and inversely proportional to the square of the distance between them. This simple yet profound statement encapsulates the essence of electrostatic interactions. Imagine two tiny spheres, each carrying an electrical charge. If both spheres carry like charges, they will push away from each other, repelled by an invisible force. Conversely, if the spheres possess opposite charges, they will experience an attractive force, pulling them closer together. Coulomb's law allows us to calculate the strength of this invisible force, revealing the intricate dance between charged particles that governs the behavior of matter at its most fundamental level. Coulomb's law can be expressed succinctly in the following mathematical form: F equals K times the absolute value of Q1 times Q2, divided by R squared. Don't let the symbols intimidate you, they represent the key players in this elegant equation. Let's break down each term and understand its significance. F represents the electrostatic force between the two charges. This force can be either attractive or repulsive, depending on the signs of the charges involved. K is a constant known as Coulomb's constant. It ensures that the units of our calculation align correctly, much like a universal translator bridging the gap between the abstract world of mathematics and the physical reality of electrical charges. Q1 and Q2 represent the magnitudes of the two charges interacting with each other. The larger the charges, the stronger the force between them. R denotes the distance separating the two charges. As the distance increases, the force between the charges weakens rapidly, highlighting the inverse square relationship at the heart of Coulomb's law. Coulomb's law isn't confined to the realm of theoretical physics. Its influence permeates our everyday lives, often in subtle ways we rarely notice. Consider the simple act of rubbing a balloon against your hair. This seemingly mundane action generates static electricity, causing your hair to stand on end as if defying gravity itself. What you're witnessing is Coulomb's law in action. The friction between the balloon and your hair transfers electrons, creating an imbalance of charge. As a result, your hair strands, now carrying like charges, repel each other, creating the familiar static effect. This same principle explains why clothes cling together after being in the dryer, or why you might receive a mild shock when touching a metal doorknob on a dry day. These everyday occurrences, though seemingly trivial, highlight the pervasive influence of Coulomb's law in our world. Section 5. Calculating the force. A practical example. Let's delve into a numerical example to solidify our understanding of Coulomb's law. Imagine two tiny spheres separated by a distance of 0.1 meters. The first sphere carries a charge of positive 2 microcoulombs, while the second sphere possesses a charge of negative 4 microcoulombs. To calculate the electrostatic force between these spheres, we employ Coulomb's law. F equals K times the absolute value of Q1 times Q2 divided by R squared. Plugging in the values, we get F equals 9 times 10 to the 9th Newton meters squared per Coulomb squared times the absolute value of 2 times 10 to the negative 6th coulombs times negative 4 times 10 to the negative 6th coulombs divided by 0.1 meters squared. After performing the calculation, we find that the electrostatic force between the spheres is 7.2 newtons. The negative sign indicates an attractive force, drawing the spheres towards each other. Section 6. Beyond Coulomb's law, the electric field. While Coulomb's law elegantly describes the force between 2 point charges, it has limitations when dealing with more complex charge distributions. To address this, physicists introduced the concept of the electric field. The electric field is a region around a charged object where it exerts its influence on other charges. It acts as a mediator, allowing charges to interact with each other without being in direct contact. Imagine a single charged particle placed in space. This particle creates an invisible field around itself, extending outward in all directions. Now if we introduce another charge into this field, it will experience a force due to the presence of the field, regardless of the distance separating the two charges. The electric field provides a powerful tool for visualizing and analyzing the interactions between charges, especially in complex systems. Section 7. Pushing the boundaries. Gauss's law. Building upon the concept of the electric field, Gauss's law offers an even more powerful tool for analyzing charge distributions. This law, named after the brilliant mathematician Carl Friedrich Gauss, relates the electric flux through a closed surface to the total charge enclosed within that surface. In essence, it provides a way to determine the electric field created by a charge distribution without having to calculate the individual contributions of each charge. Imagine a spherical surface enclosing a point charge. Gauss's law tells us that the total electric flux through this surface, which can be visualized as the number of electric field lines passing through it, is directly proportional to the enclosed charge. This elegant relationship allows us to calculate the electric field for various symmetrical charge distributions, simplifying complex problems and offering deeper insights into the nature of electrostatics. Section 8. From static charges to dynamic currents, electromagnetism. Coulomb's law, though primarily concerned with static charges, laid the foundation for a much broader field of study: electromagnetism. As scientists delved deeper into the nature of electricity and magnetism, they discovered an intimate connection between the two seemingly disparate phenomena. Moving charges, or electric currents, were found to generate magnetic fields, while changing magnetic fields, in turn, induced electric currents. This groundbreaking realization, culminating in James Clerk Maxwell's elegant equations, unified electricity and magnetism into a single fundamental force, revolutionizing our understanding of the universe. From the generation of electricity in power plants to the operation of electronic devices that permeate our lives, electromagnetism stands as a testament to the far-reaching implications of Coulomb's law. Section 9. The enduring legacy of Coulomb's law. Coulomb's law, though seemingly simple in its formulation, has had a profound and lasting impact on our understanding of the universe. It serves as a cornerstone of electromagnetism, providing the bedrock upon which countless technological advancements are built. From the design of electric motors and generators, to the development of sophisticated medical imaging techniques, Coulomb's law continues to shape our world in countless ways. As we venture further into the 21st century, facing unprecedented technological challenges, a deep understanding of Coulomb's law and its implications remains as relevant as ever. It serves as a reminder that even the most complex phenomena can often be traced back to fundamental principles, underscoring the elegance and beauty of the laws governing our universe.